Well, welcome to the problems from Chapter 6 of Fundamentals of Particle Technology. This is problem number 1. It's a bit of a complicated problem. There's lots of text in the book regarding the problem, so unusually I'm going to solve the problem in the way that I don't normally. I'm going to show a diagram to start off with and then explain what's going on within the diagram. It's batch settling, batch sedimentation. That's what it's all about, and it's an initial design scenario really. We have a feed, or potentially we will have a feed going into a tank, and the feed is 1,000 meters cubed per day of a suspension, and that suspension is 3% by volume going in. So that's volume of solids divided by total volume, 3%. So clearly that implies that of the 1,000 meters cubed that goes into the tank every day, we have 970 meters cubed of liquid, and that liquid is water, okay, and 30 meters cubed of solid, and that will give us our 3% by volume. Okay, so that's what's going into the tank just here. The intention is to operate the process such that the materials allow us to settle, to sediment, hence we end up with this sediment just here, and we like to recycle to the process some of the water. We'd like to recycle as much as possible, and the design requirement has been set at 85%. So we're trying to recycle 85% of the water each day back into the process. Okay, so that will clearly leave all the solids from each day plus 15% of this 970 meters cubed left in the tank. And you'll notice the pump that sucks out the water, because the water is leaving in that line just there. The pump that sucks out the water, the line rather that sucks out the water, has this sort of U-shaped bend to it, so that water flows in from the top. We're trying to avoid sucking in solids from the sediment. Okay, so it's a 3-day cycle. So day number 1, material is put in here and it sediments, followed by sucking the liquid out. Then day number 2, material is put in here, same process, and material is sedimented out. And then finally day number 3 is the last batch, and sure enough the tank's going to become too full to carry on. So at the end of day number 3 everything has to be removed. So there is in fact a drain down here as well, which we would operate on day number 3 in order to remove material from the tank, and clearly that would be a normally closed valve, other than the removal bit on day number 3. Okay, so that's the intention. It's clearly a very cheap way of trying to separate the water from some solids, from some slurry, which can then be taken off and presumably to filter or some other way of recovering the liquid. So it's a batch tank, and this is the design. Does it work? How would you design a tank? How big a tank would you need is essentially what the question is asking. Okay, well, before we look at batch sedimentation and what goes on in batch sedimentation, let's just do a few calculations, because the most difficult day, in other words, what we're going to have to effectively design this tank for, is day 3, when it's at its maximum capacity. And on day 3, we will have inside the tank 2 lots of 15%, or 0.15 times 970 meters cubed of water plus of course the third day's worth of water, which is 970 meters cubed as well. So that will be the total volume of water on day 3. Okay, so this is day 3. So I better bracket that out so it doesn't look like it's part of the calculation. In terms of solids, that's much simpler, because in terms of solids we're just going to have 3 times 30 meters cubed of solids. So if we put all our equals over here, that's clearly going to be 90 meters cubed of solids. And if we work out turn to the trusty calculator, that's 0.3 times by 970 plus 970, which is 1261. I'm going to call that, well, I'll call it 1261. We'll drop the 1 later on though, I'm sure, because it's such a small amount. Okay, so the total volume we have that's present is that plus 90, which is 1351. I think I'm going to call it 50, to be honest, just to make life easier. Let's call that 0. It's near enough. It's approximately equal to. And that means that the solids concentration on day 3 is going to be equal to 90 over 1350, which is 90 divided by 1350, 6.7%. So we're talking about 6.7%, because it's 0.067, so 0.67%. And that's volume to volume again. So we're designing this tank really for day 3, where we have a 6.7% solid concentration settling in a total value of 1350 meters cubed of slurry. Okay, so that's essentially what the design requirement is. Now let's talk about batch sedimentation. So if I move this down a little bit, I'll put in the rubric underneath the video a link to some pictures of batch sedimentation, but I want to just demonstrate here what's going on inside the process of batch sedimentation. So what we have here is, this is the height of the interface. Okay, and there's a clear visible interface. It's just about here. Just jump back up to the top, and you can see the particles are in hindered settling. The particles are getting in the way of each other, and it's settling en masse. And we can see the interface has just made it to my arrow roundabout now. So the concentration in this area just here is the same as the original solids concentration, which is 3% in our particular question. So initially we've got 3% solids settling until we get to the point where the solids all come together, and it's settling in a straight line. The height against time graph is settling in a straight line because that's the region of the original concentration. We'll call that C0, which is 3%. However, as we're settling, clearly we must be initiating a solids concentration greater than 3% somewhere inside the tank. Let's call that 3.1%. Where does that occur initially? Well, initially it's got to occur at the base. It can't spontaneously occur anywhere else, it's got to occur at the base. And if you were to track that 3.1% concentration up the tank, you'd find that it was a straight line. There we go. That's the 3.1% line that starts at the base and comes up and eventually meets with the settling interface just there. So that's where our 3.1% concentration meets the settling interface. But it doesn't stop there, because as time goes on, that's the time when we've got 3.1% at the interface, but as time goes on, it's replaced by another concentration at the interface, and then another, and then another. Hence you get this whole collection of what's called characteristics, which go from the base to the settling interface, and of increasing concentration. So we start off here at 3.1%, but then it's 3.2%, 3. Blah 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 blah, until you get up to the final settled sediment concentration, which could be something in the order of 20% by volume, might even be 50% by volume if you have something that's very incompressible. So that's essentially what the batch sedimentation looks like, with this constant rate to start with, and these characteristics which you clearly can't see because it's all just a mess under here. You can't actually see these characteristics, but the characteristics, if you were to just consider a fixed concentration, are doing this uniform increase in terms of height and time until they reach the interface just there. So that's what's happening. Okay, so let's just pause that a moment. Okay, so that's what's happening in batch sedimentation. Now I'm going to go to the actual online questions and do the worked solution using the online questions, because there's a lot of graphical constructions involved in this. So rather than use my scratchy handwriting and pad, I'll do base it all around the online. And this basically just goes back to saying there's a 3% suspension to be settled in a tank. Here is the settling data, having taken a sample of this material and settled it in a 1 litre measuring cylinder. Okay, so it's settling in a 1 litre measuring cylinder. Here is the height against time data. And if we move on, then that's what this looks like just here. We have something just below 30 centimetres. In fact, it's 28 centimetres. So it starts at 28 centimetres, and then the settling goes on and comes down here. And the person who took the data hasn't bothered to let it fully settle out, and frankly, it doesn't matter. So let's have a look at some questions. It says here, it's proposed to operate the settling tank on a 3-day cycle. 1,000 metres cubed of suspension is run into the tank each day. It's allowed to settle, and then some liquid is recycled back to the process. At the start of the 3rd day, 85% of the liquid from the first 2 days has been recycled. The total solids volume in the tank after addition of the suspension on day 3 is 90 metres cubed. Yep, that's what we worked out. Prior to removal on day 3, the total liquid volume in the tank is, well, that was 1260 when we calculated it a few moments ago. So I'm going to select 1260 and we'll just check that that's the right answer. I'm glad to say, yep, that's the right answer. Good, good. So we can move on, right? So we have 1260 metres cubed of water in the tank, 90 metres cubed of solids at the start of settlement on day 3. It may be assumed that the action of adding the suspension on day 3 completely mixes the tank to give a uniform suspension with the concentration of, well 90 divided by 1260 is 0.067, so the concentration on the 3rd day is going to be 6.7%. Quick check, yep, we've got the right answer. That's brilliant. If by some means we'd clicked on the wrong answer, then it would tell us what the right answer is. Although, to be honest, that doesn't. Oh, it is. Yeah, the correct answer was A, and it gives you the reason why. It's that 90 divided by 1260. So there is the online solutions do give you the answers to the problems. Okay, let's move on. Okay, so here is our settling curve plotted out. Here is our characteristic that we've just been talking about. This would be the characteristic which is at a particular concentration that we've yet to calculate out, because what we have here is a material balance. It's not terribly clear, but this is saying that if you have a concentration some value multiplied by a height, so initially our starting value would have been 3% by volume times by a height of 28 centimetres times by the area, that would give us a meters cubed of solids, and then that would be equal to another concentration times by a height times by the area, again meters cubed of solids. As the batch cylinder contains solids that haven't been moved or diluted, then it must be the same volume of solids, and that's just a material balance, so we can work out different heights for the same amount of solids if we know what the different concentrations are. Okay, so how does that work? Well, we know we started out with a 3% suspension of solids at 28 centimetres, okay, and then came down here, and we can, by our material balance, work out the same, for the same amount of solids that's present, we can work out what the starting point would be at any arbitrary concentration you wish to choose. We know that the arbitrary concentration that we need to choose is 6.7%. So what would a 6.7% suspension settling look like? Well, it would start out at whatever the material balance tells us the height should be, okay, and from this diagram the answer is already there. It's 12.6 centimetres. So 12.6 times by 6.7 is going to be equal to 3% times by 28. Okay, so that's coming from the material balance that you see written just here. Okay, so if this was the 3% settling curve, and then this is the 6.7% settling curve, they come together at some point, and then they carry on at exactly the same curvature, because the solids, it's the same amount of solids there. It doesn't know whether it started at 3% or whether it started at 6.7%. It's the same amount of solids. They'll have the same performance after they've come together. So the material balance says what height do we need? Well, we know that's 12.6 because that's come from our material balance just here. Let's just check. Correct, that's good. Okay, let's move on. Because don't forget, we're designing this process for a material settling at 6.7%, that's the pinky curve here, rather than material settling at 3%, okay, because that was the initial amount of material. Okay, so it says that we take your ruler and draw a line from the height determined, which is 12.6%, to draw a tangent to the curve, because the curves have to be the same. Where does it actually come together? At what temperature? At what time does it come together? It comes together, actually, I think, by the look of it, at 180. But I could be wrong. It might be 220. Let's have a look. It is correct. Okay. So at 180 minutes, the two come together. The settling curve from 3% and the projected settling curve from the 6.7%. They come together at 180 minutes. Okay, that's good. Right, and then it continues to settle. Right, okay. As settling rate is independent of vessel diameter, one design is to construct a vessel of height given in part 4, i.e. 12.6 centimetres. The total vessel volume would need to be sufficient to accommodate the volumes given in part 2, in other words 1,350 metres cubed at the start of the third day's sedimentation. This would make the vessel area, so you're looking for a volume, so one of these areas times by 0.126, because that's the height, will give you this value of 1350. In other words, 1350. So which vessel area times by 0.126 gives you the value of 1350. I think it's going to be a biggie. I think it's probably, oh, there's answer D. Okay, that one there. So 10,700 times by 0.126. Just do check. This is a check. 10,700 times by 0.126 gives us a volume of 1,350, near enough, within rounding. Okay, so one design, to answer the question, one design is to start off with a tank that's 12.6 centimetres high, well, for the final settlement, and to allow it to settle for a certain amount of time where we can get the liquid out, and the area on that would be 10,700 meters squared, rather large area. Don't forget this 28 centimeters here is what the height is in the measuring cylinder. We're not suggesting necessarily that we need a 28 centimeters high settling tank. That just happens to be the measuring cylinder. Whereas to do the design for the big tank, we could get away with a 12.6 centimeter high tank with that area. It's obviously a silly value. There is no way you're going to use such a small tank with such an enormous area, but we'll see that in a minute. Okay, at the end of the settlement period on day 4, after pumping the supernatant, but before pumping the sediment out, the volume of sediment is, on day 4 we'd have to go back to a material balance to work that out. If we go back to our material balance, which we had just here, we know we're going to have 90 meters cubed of solids, and in fact we can do 3 times 0.15 times 970 to tell us what the volume of the liquid is that's left in the sediment. So that's 3 times 0.15 times by 970. That's 437 meters cubed. 437 meters cubed of liquid. But of course we have also 90 meters cubed of solids, so that's 527 meters cubed. 27 is 26.5, but 527 meters cubed. That's total volume of slurry. So let's go back to where we were. 527 meters cubed. That's sediment after pumping supernatant before putting out the sediment volume is that. Ready to answer? 527. Yep, good. Move on. Okay. So we have 527 meters cubed of sediment, and if we were to use the theoretical area that we just previously discovered, we can work out the height of the sediment when the characteristic meets the settling curve. Okay. So in other words, that is the characteristic that we're focusing on. It's the one we know we've got, because we're interested in the water that sits above that settling curve. That's what we'll be pumping back into the process. So we've done a material balance to work out where the height it will be, and the height required for the sediment is about oh, this is in meters, is going to be around about 5. Let's just check that. Correct. Yeah, around about 5 centimeters, 0.049. Let's call that 5 centimeters. So above that settling curve, that's where that's all sediment. Above that settling curve is the liquid. If we could pump all that out, we would fulfill our requirement of 85% recycle before we let the sediment just drain away. So that's leaving the sediment in the tank for 220 minutes. We've now got a good design. It's a rubbish design from the point of view of being practical, but a theoretical design that would work. We could have a tank that's 12.6 centimeters high. We can let it settle for 220 minutes. After 220 minutes on day 3, we can pump out all the supernatant liquid down to that particular height of 5 centimeters, and then the other material below that, the sediment that exists from 0 to 5 centimeters, is what we drain off the tank. That is one design. Okay, technically speaking, that is possible. Mathematically, that doesn't breach any continuity or anything like that. Move on. So the next question is, okay, it happens to be 220 minutes that we're leaving it for. We can see that from the diagram. Let's move on. So the question now is, have we finished? Is it job done? Do we need a shorter tank? Do we need to add more solids before settling? Well, I don't understand why that's an option, to be honest. Do we need a taller tank? Designing a process to work with such a small tank is clearly ridiculous. So we need a taller tank. Correct. We've shown that following the material balance, following the settling, the sedimentation theory, we can design this tank, but there is no way in practice it's going to work. So we really do need a taller tank. So how are we going to work out what a taller tank would look like? Well, we have an almost infinite set of results here, because it depends on which characteristic you want to consider. How long can you leave it to settle? We've worked out that the minimum is 220 minutes, but of course we could leave it for longer than 220 minutes. It will have settled down further, and if it settles down further, we could have a less wide tank and a taller tank, which is clearly what we want to have. So the question becomes, how long can we let it settle? Well, how about 24 hours? We know that this is on a daily cycle, so 24 hours is the longest time that we can leave the thing to settle. So this is assuming that we can leave it for 24 hours, the height of the characteristic, if we're going to carry on looking at this characteristic that worked for initial design, which we didn't like, but we're just scaling the thing up now. If we leave that for 24 hours, how high will it be? Well, 24 hours is 24 times by, 24 hours times by 60. Okay, and then if we divide that by 220, that gives us a value of 6.5 times what we had originally calculated the height to be, which was about 5 centimeters. Thus the height of the characteristic after 24 hours, so that's times by 0.049, near enough 5 centimeters in other words, gives us 32 centimeters. So after 24 hours, that characteristic would be at 32 centimeters, correct? Good. So we could actually change the tank to be 1/3 of a meter high for the sediment, right? The new vessel area required to accommodate the total sediment on day 4, if we're now looking at the same volume of sediment, so if we nip back to this 527 meters cubed, so 527 meters cubed of sediment, and it is 0.32 meters in height. So what's the area times by, so which one of these times by 0.32 gives us 527. Quite honestly, I don't know, and I'm going to take the easy solution. The correct answer was A. We've brought the area down to 1650. Okay, so 1650 times by 0.32. Let's just check that. 1650 times by 0.32 equals 528 meters cubed. So that's our volume of sediment. So we brought the area down dramatically. It's now just 1650, and we're using a vessel height which is 0.32 meters, 32 centimeters. It's still not good enough, really. We know that we can fulfill the requirement for the sediment at that height, but the total vessel height has to accommodate everything. So that's 1650 meters cubed. I mean, clearly we're heading in the direction of a tank that's going to be too short. The correct answer for the total height of the tank, I think, is going to be something like 0.82, which is correct. So that would be the height that we would need to accommodate the 3% suspension at the start. It's still less than a metre. Clearly this is not a practical design. There's no way that that's a practical design. So we have to have an alternative strategy, and that alternative strategy would not to be a batch settling tank as was drawn here, but a continuous thickener where we're continually taking the liquid out, because in order to fulfill our design requirement, this design requirement of 85% of the water recycled, the maximum height that the tank is filled to would be 0.82 meters. It's not good enough, because if you're pumping 1000 meters cubed per day into the tank, it would be sloshing about quite high, and we're looking at a height down here of, I think it was about 0.12. No, this system here, designed to take the supernatant off, doesn't have that higher level of precision. We can't work to that higher level of precision. Instead of having a tank that's a batch tank, what we really need to do is enable continuous offtake of the material, of the underflow, which will have the sediment in, and the overflow, which will have the clean liquid. And that is what a continuous thickener is, and that is what's looked at in the next question. Okay, thank you.